Okay. Uh, Hi everyone. Welcome to the another session of book club on designing data intensive applications. Uh, Today we will continue our discussion on the chapter consistency and consensus. Uh, so the topics we will be going to discuss today is fault tolerant consensus. Uh, so we will see one of the examples of fault tolerant consensus in Raft, that how Raft implement uh, fault tolerant consensus. Then we will see the basic fundamentals and principles behind building fault tolerant consensus that are shared among Raft and other similar algorithms which implements fault tolerant consensus. Uh, then, if we have time, we can discuss about some of the membership and coordination services that use fault tolerant consensus and provides other services like Zookeeper. Okay, so last time we were discussing this visual of Raft and we were hoping to understand it so that we can better understand the text behind the fault tolerant consensus. So let's continue and finish that so that then we can jump into the theory behind it. So this it was talking about a single, yeah. So basically, uh, consensus means that a group of node they should jointly agree on something. They should jointly agree on a value, right? And we discussed that in draft. The way it is done is by electing a leader. So uh, So a node could be in one of the three states, either a follower, a candidate, or a leader, right? And so all of the nodes are initially in the follower state. If a follower doesn't hear from leader, they can become a candidate. So this node has become candidate, and the candidate will request votes from other nodes. Uh, Nodes will reply with their votes. If it gets a majority of votes, then this node will become leader. So in Raft, now the all the communication from between the client and this network will happen through this leader node. So now this candidate has become leader. Uh, so now if a client sends a request that it wants to replicate this log set 5, then data will take this value, it will write it the value, but the value is still not committed. uh, then this change will be sent to all the nodes, right? uh, so these follower nodes will also write the data on them, and when the leader gets the vote from majority of the nodes, then the leader will commit this value and it will respond back to the client that your write was successful. And then it will also send the entry is now committed on the leader and the node state is 5. And the leader then also notifies the followers that the entry is committed. So now the value on them, on the followers also has been committed. So last time we were discussing various scenarios. So one of the scenario was that if the leader, so when the leader has sent the request to write this log and this log was in uncommitted state in these two nodes, at that point, let's say if the leader dies, right? So what happens in that case? So in that case, these two nodes have set 5 in uncommitted state, and now we don't have a leader in the system. So there will so the leader election will happen in the system. One of the nodes will become leader. So let's say this node becomes leader. Now then, uh, this node will see that this value of set 5, which is an uncommitted state, so is also same as in other node. So it will see that like majority of the nodes in the system have this value in the uncommitted state. So then it can say that this is the correct value. So it will commit the value. So then this value will be committed by the new leader, and this data will be stored. So even if after uh, after committing the value and responding to client, if the response does not reaches these nodes, still the data will be stored in the system, because when one of them will become leader, they will commit the value. Okay, so the cluster has now come to consensus about system state here. So this process is called log replication. so so the process of leader election is, so in RAF there are two timeout settings which control elections. First is election timeout. So the election timeout is the amount of time a follower waits until it becomes a candidate. The election timeout is randomized to be between 150 milliseconds to 300 milliseconds. So now the election timeout will happen between one of the nodes. So it happened here. So after the election timeout, the follower becomes the candidate and starts a new election term. And so the term will be an incremental value of what was the term it had before. So initially all of them had term 0. Now when when the election timeout happened on this node, it will increment the term. So now the term has become 1, right? And so this node first it will vote for itself, and then it will request vote from other nodes. So if the receiving node hasn't voted yet in this term, then it votes for the candidate. So these two nodes, they haven't still voted for anyone else in the term 1, right? So they will vote for this node. And these nodes have also resetted their election timeout after they have voted, uh, basically to let them know that now someone else is trying to be a leader, so they can reset their election timeout. So, and now it has got vote from like 3 nodes out of 3, which is a majority, right? So this becomes the leader now. So now this node C is the leader for term 1. So this is the term ID for term 1, node C is the leader. And once it becomes leader, then all the communication will happen through the leader, and it will send append entry messages to its followers, right? This is what we have discussed. These messages are sent in intervals specified by heartbeat timeout. Okay, so one thing was the messages, and also the other thing is that even if there is not any message, then still the leader will send these nodes heartbeat timeout. So these heartbeats are telling these nodes that there is a leader in the system. So as soon as they receive this heartbeat, they will reset their timeout because they are let they have been known now that there is a leader in the system, so they can reset their timeout. And also this, if there is any append entry, like if there is any log message which has to be replicated, that is also sent in this heartbeat. So uh, so then followers will respond to each append entry message, so like they're responding here. Okay, so yeah, so the election term will keep on happening. So the leader will keep on sending heartbeat messages. Those heartbeat messages, either they would have these append entries if the client has sent any request, or they could be these like they could not have any new message, but then the clients will be responding back, right? So this will keep on happening until a follower stops receiving heartbeat and become a candidate. As soon as any of the followers does not receive this message, it will become a candidate because it will think that there is no other leader in the system. So like let's stop the leader and watch the re-election happen. So now this node has stopped. So election timeout will happen on one of these nodes. This node. So this node voted for itself, and this node also voted. So it got two votes. It incremented the term. So term became from 1 to term 2. And now this is the leader. So node A is now the leader for term 2. So requiring a majority of votes guarantees that only one leader can be elected per term, right? If two nodes become candidates at the same time, then split vote can occur. Let's look at the split vote example. So in this example, these two nodes, so initially term was 3, and these two nodes, they become leader, they become candidate for term 4 simultaneously. So they initially voted for themselves, so their vote count is 1, and now they will request these 3 other nodes asking their votes, right? So and each reaches a single follower node before the other. So like if this node receives a message to vote from these two nodes, uh, whoever's message comes first, it will vote for that, right? Because we said that a node will only vote once in for this term, right? So it will they will respond back to one of them. uh, but now it can happen, like let's say on this node the message came first from this candidate, and on this node the message came first from this candidate. So this will also have two votes, one for itself, one from him, and one from itself, one. So both have two votes now, right? Total. So each candidate has two votes and can receive no more for this term, right? Because they have already voted, so they will not give them any more vote. So then, because they it could not be decided, because to become a leader you need majority, right? You need consensus. So then none of them will become a leader, and like again a timeout will start, and then again voting will happen. So now node A received a majority of vote in term 5, so it became a leader. So basically, because this timeout is randomized, so like even if at some point, at some chance, it could happen that two nodes can time out at the same time and can send votes, but when again this thing will happen, because of randomness, it's hard that there are like very less chances that the problem will repeat again, because one of the nodes will have a lesser timeout, one of them will have more. So basically only one of them like should be able to become a candidate first and collect the votes for that term and then become a leader.
Abhishek,
Yeah.
I, previously you say node A received 2 vote and node B received 2 2 vote. How
Yes.
could they receive 2 vote? Because uh, one node only vote for one candidate, right? If they already vote, they're not gonna vote again, right?
Yeah. Yeah. Right.
So how could they both receive two vote?
So yeah, so what happened was this node was a candidate and this node was a candidate, right? And these two
Right.
were for followers. So this node, so this node sent the message to all these three nodes, right? Now, when the message came from node A to node B will not respond with its vote because it is also a candidate, right? So it will not. It has already voted for itself in the term. So the rule we have said is if a node has voted for someone in the term, it will not vote again. So node B has already voted for itself, so it will not respond back to like it will not give node A vote. On node D, it the message came and node D has still not voted for anyone. So node D will give him a vote, right? So now node A has got one vote from itself and one vote from node D. And now node A was going to send also was going to ask vote from node C. But before the vote request came to node C, the vote request from node B came first. And now because node C has still not voted and it got the voting request from node B, so it will give its vote to node B, right? And now when the node A request reaches, because node C has already voted for node B, so it will not give its vote to node A because it has already given one to B. So now you will see that node B has got vote from node A has got vote from node D. And similarly, node B will also try to get vote from node D, but since node D has already voted for node A, so it will not give its vote to node B, right? So both of them have got two votes, one their own, one from this. Node B has its own, and one from C. So this is a scenario where a split vote could happen,
Yeah, got it. Thank you.
right? So node A received majority of votes in this term, so term 5, and now it became a leader. Okay, so log replication. So once we have a leader, then the leader will replicate all these changes to all the nodes in the system, right? Okay, this is done by using the same append entry messages that was used for heartbeat, right? So heartbeat is also being used to tell that there is a leader in the system and also to append these entries, which could be the messages which are sent by clients that have to be replicated among all the nodes in the system. So let's walk through a process. So first a client sends a change to the leader, right? So it will say set 5. The change is appended to the leader's log. Then the change is sent to the followers at the next heartbeat. So at the next heartbeat, in the heartbeat now they have this message set 5. An entry is committed once a majority of followers acknowledges it, right? So now this value is committed here. So it's black, right? And it is still uncommitted on these followers. So now when it has got a vote from majority, it will make the decision that this values can be committed. So it will reply success to the client, right? And also it will send a command. Yeah, and then it will also send the request to commit this log to both of these followers, right? So that was this. Now I think the second command is that the log has to be added to 2, right? So the same thing happened. It first they both were sent a write log, and then the decision was made. It was committed in leader, and then it was committed in the followers. So now like any state machine can look at these logs and calculate the value, whatever value has to be calculated, right? So set 5 and add 2, so all the nodes have the value as 7.
Abhishek, I have a question. Why not to send request to commit for two followers before send acknowledge to leader to click to client?
Mm, so because then it will add more delay, right? Because so if we uh, first we send to the client, first we send to followers that this write this message, and we receive a vote, and then if we again send a message and wait for them to get committed and then respond back to client, then it will take more time to respond to client. uh, and the system can still work without waiting for the commit acknowledgement from the clients. So that's why I think it makes sense that like to respond to the client sooner. Like if we can make the decision sooner, right, then we will choose to make the decision sooner so that the client does not have to wait. Do you have any scenario in mind which you think like this could create a problem? We can discuss that.
No, I don't have such a scenario.
Yeah, so then yeah, like we will try to do something as soon as possible if it right. Otherwise the client would have to wait more if we send the message to the followers first. I think that's the reason.
So uh, the sets and adds are going to the master. So if there is a get, uh, can I call the? Uh, does it have to go to the master itself, or slave also can be possible?
Yeah, I'm not very sure about it, but so my understanding is that like if you want, like if you are okay to read stale values, then you can ask the values from any of the followers. But if you want like most up to date value, then you would have to go through the leader and then receive the value which is up to date. So in your ride, it's up to you that do you want the most up to date value, or are you okay to read the stale values? Okay, so moving on. Yeah, so this is very interesting. So Raft can stay consistent in the face of network partition. So now, like, we have 5 nodes, right? And this is the leader, and this is the term, right? Uh, so now let's see. Now they have added a partition between these 2 nodes, right? So now there is no leader between these 3 nodes, right? And so the election timeout will happen in these 3 nodes, and so this has now become a leader. So now the term of this node is 2, and term of this node is 1, right? And basically now we have these two leaders, right? There is one leader over here, one leader over here. So now let's see how the system will work now. Because client talks to the leader. So now basically it could happen that like in this partition, like the client is talking to this leader, and in this partition the client is talking to this leader, right? So when the client will send the value to set 3 to this leader will send this entry to its follower, and it will wait for the majority of them to acknowledge before it can commit. But it has got the vote from only 2 nodes. So basically, to to elect a leader, also we need a quorum, and also to commit a value, we need a quorum, right? So now we already have a leader, but to commit this value 3, we needed a quorum, but it will get vote only from one of the nodes, right? So it has only 2 votes. So that's why this value will not be committed. So this set 3 will be left in uncommitted state. Node B cannot replicate to a majority, so its log entry stays uncommitted, right? And for this, if a client is talking to this node, it can successfully replicate it among the majority of the nodes. So this system will work fine. Upper system will work fine, right? The other client will try to set the value of node to 8, and this will be successful because it can replicate to majority, right? So now when the network partition is healed, so then this leader will send the heartbeat messages to all the nodes, right? And node B will see the higher election term and step down. So node B will see that there is a node which has a higher election term, right? So it was a leader, but it saw it received a heartbeat from a node which has higher election term, so it will step down as the leader. And also all the uncommitted log which these nodes have, they will be overwritten. So in the heartbeat, they will also have like what is the latest log entry and the message. So with that message, these will be overwritten, the previous values which were uncommitted. So both nodes A and B will roll back their uncommitted entries and match the new leader's log, right?
How would they roll back their roll back uncommitted entry? Okay, right. So they never commit any entry when the network partition happen, right? They might receive the request but never commit it.
Right. Yeah.
Yeah.
So they never committed the value, and so let's say before the network partition, all the nodes have log entries till index 2, right? And now they had this at index 3, they had that uncommitted value, right? So now when this leader will send the heartbeat, it will say that the log index is 3 and this is the value. So these 2 nodes will see that at our index 3, we have this uncommitted value. So we can remove our entry, and whatever the new leader has sent in the index 3 as the new value, we will commit that value. So they will commit that value. If they were, like, if the system had reached much ahead, like if it had the logs till index 5 and they had logs only till index 3, then they will ask repeated, like then the leader will send those message back, like whatever messages they did not have, it will repeatedly talk and send all those messages which these nodes did not have with them. So, and so
what would happen to the client of node B and node A? When the network partition, that client received stale data, right? And now the network partition is healed. Then do they get notified, or they still receive they still have stale data?
So if you're talking about this client, when it was trying to write the value, its request was it did not receive a response as success, right? So its value, like it did not receive the success. And now when the network partition has healed, n- so we like this overall system is not visible to these nodes. They can only talk to the leader, right? So now when the network partition has healed, this node can also only talk to this node D, which is the leader.
Mm.
So that's why like things will work fine. Did I answer your question?
Yeah.
Okay.
So they don't know the network is partitioned until like
Yeah.
they talk to node D, and then they know they get the up-to-date value.
Yeah, and I think actually they don't talk directly. Like there is some, I think there would be some system like some place where that the IP address of leader is this. So first this node will get the IP address of leader, and then whatever IP address is, it will contact the leader through that IP address. So whenever the leader is updated, that IP address is updated. So when there was a network partition, then like this node thought that that IP address is of node B, and it was talking to node B because it thought the leader is that. But when the network partition was healed, that IP address was updated to node D's IP address. So then now it started talking to node D.
I have a question. Can client ask any node so that node provide IP address of a leader, of current leader? Is it part of protocol to so that client can ask any node in order to receive a leader IP address?
Yeah, I think, yeah, I don't know. I don't know exactly how they implement it, but yeah, that is also possible that because each of these node agree who is the leader in the system, right? So basically each of the nodes can also store the IP address of the leader because each one of them have agreed. So now the client can talk to any of the followers in the system, and then follower can give the IP address of the leader and then send the message to the follower and then get. Yeah, I think that is also possible, and I don't know exactly how Raft implements it, but yeah, that seems possible. That could. Okay, yeah, so our log is now consistent across our cluster. Yeah, this was the secret lives of data. So now with this, I think we can come back to this. Yeah, we can come back to fault tolerant consensus, which has been discussed in this book. So yeah, so a fault tolerant consensus must satisfy these four properties, right? So these four properties are uniform agreement, integrity, validity, and termination. So let's understand this with the example. So let's say we have a group of friends, right? And a group of friends, we want to discuss that what we want to do on a Saturday evening, right? So, and so let's say we want to agree on one of that thing that we want to do so that we can do that thing, right? So basically, by consensus, what are we expecting from that overall system? That if someone has proposed that, hey, let's go to movie, someone has proposed let's go to dinner, we all should agree on one of the values so we can do that thing together, right? So the first property, uniform agreement, that everyone should, like, overall, after the discussion has finished, overall there should be one agreement in the system that everyone should agree that okay, we have decided to do this, right? And integrity. So integrity is like once someone has decided that okay, we all will go to movie, now it cannot, like, while now the plan has happened, now it cannot change its decision and say, hey, that no, I don't want, I want to go to dinner or something, right? uh, and validity. So validity means that if someone has decided a value, then it has to be proposed by someone. And in these system, that value is proposed by a leader. So first a leader is elected. So basically we can consider in this system that initially we will have a leader, and whatever the leader says, the nodes will agree or disagree with the value, like whatever value the leader has proposed, right? And the fourth property is termination, that everyone, if they have not crashed, like if they are not sleeping or something, they will respond back and give their vote. They cannot say that we will not vote, right? So every node that has not crashed eventually decides some value. uh, and then, so the thing here is how it is different from two-phase commit is that in two-phase commit, we wait for all of the nodes to reply yes, and then we can say that we have to commit this log. But in this fault tolerant consensus, so basically that's why we saw that two-phase commit is not fault tolerant, right? That if one of the node is not available in the system, then the value will not be committed, and 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 so the and so the yeah, so the system will not be able to any further commit the values. But here in fault tolerant consensus, we need vote from only majority of the nodes. So even if some of the nodes are down, still we can reach a decision, right?
Rishik, I have a question. Does it mean that fault tolerance means that leader will be re-elected in case of leader crash? It's so re-election of leader means fault tolerance.
Yeah. So fault tolerant means that basically the meaning of fault tolerant is that as long as the majority of the nodes are live in the system will continue to work fine. And now the nodes which have gone down, those nodes could be either leader or follower or candidate. Like it could be any node. If a leader node goes down, then the leader re-election will happen. If a follower node goes down, then the follower will not get those append logs because it is down, it will not receive the messages, but still your system will work fine. So the system just says that you should have majority of the nodes working fine, and as long as you have majority of the nodes working fine, the system will continue to make progress.
So another thing different between two-phase commit and consensus is was it like in two-phase commit we need 4 messages, right? One we send from the coordinator to our node to say prepare, and then the node reply back and say okay, they done prepare, and then the coordinator send that's a second message, and then the coordinator send a commit to each node. That's the third message, and each node reply with the commit. That's the 4 message, right? but in consensus, there's only 3 messages. Is that correct?
So, yeah, I mean, so what your point is, uh, so in this book, so I don't know that I know, like, I didn't understand why are you saying 4 and 3, but I can see 3 and 2 that in two-phase commit, it has shown that like there will be three messages sent. So one is right? This right message was sent, then the prepare, and then the commit, right? So
Yeah.
there were
So per client, like let's think of per client of the coordinator, there 4 messages, right? One sending out from the coordinator, right? And one sending back from, let's think about database 1. So coordinator send to database 1 first, that's a 1 message, right?
yeah,
And
this is one.
database 1 reply to the coordinator, that's the second message.
That is part of one message, right? That request and response. So request and response is part of one message.
Yeah, but in consensus, uh, the leader send the message to the follower, and then the follower reply back,
Mm-hmm.
and then the leaders say commit, right? One they say commit, it does not wait for the follower reply back, and then they just send, just send up, and then they send the response to the client.
So yeah, here also we can do that in two-phase commit also, that like once this prepare, if you get yes response from all the nodes, then the coordinator will write that message in its log that now the decision has is to commit the value, and it can respond back to the client saying the your value is committed, and then it can send the commit message to these node. It does not have to wait for the okay to before responding, because it has responded okay to the client, right? Now these databases, nobody can access their these rows because these rows are logged until, so at this point we said that these databases, they have agreed to commit the value, and now they cannot go back and abort, right? So now the values are in the logged state, and either if someone will reach them, these values will be logged, so they have to wait, or as long as the after the lock is released, they would have heard back from the coordinator, and they would know the decision, that the decision was to commit the value, so the database will have the right value.
So you're
But
saying it does not it does not need to either two-phase commit. It does not have to wait for the okay, the last okay from database 1
yeah,
before they send the response to the client.
yeah, it has to wait only up till this line, this point, that all of them have replied yes, and then it will write the decision in its log, and then it can respond to the client that your request is successful. It does not have to wait for this thing to finish before responding to client.
Okay. I thought we was probably a couple weeks ago we saw there's a crash right there, and the coordinator had to wait. It cannot make decision, but I
So if the coordinator is crashed, right? Let's say after this point, this thing happens, and we have responded success to the client, right? And these have still not got the message, okay message, right? And now the client have got okay response, and now the coordinator has died uh, before receiving the okay. So these rows will remain logged. So these rows will remain logged until the coordinator is back up again and they come to know what is the value of these nodes. And so that's what we discussed in two-phase commit, that so these nodes will remain logged until the coordinator is back. So that's why coordinator is a single point of failure if you have only one coordinator, right?
I see. Yeah.
And
So
that's why,
in that case, there's 4 messages, right? Like, I'm talking about a message is the one sending from the coordinator to the database one. That's one message, and database one sent back to the coordinator. That's the second message. But versus in consensus, there's only 3 messages total. So the client can receive the commit, right? I mean, the client can receive the response.
So, okay, if you are saying that you are you saying that you are considering this as 2 messages, that one
right,
being sent to okay? So there are 4 messages, one in the prepare, and what 4 are you talking about? This write and prepare, or prepare and commit?
write and prepare.
Yeah. And okay, so this is 4. Yeah. So basically, I was also thinking this, that basically this write and prepare in two-phase commit also, it could be like one message, right? It could be part of one message, that in like it could be combined into one, that in the write you are also sending the value and you are also hearing back what is the response. So if both of them have agreed yes, then and replicated to their logs, then now you know that they have agreed to commit the value. So you can also consider. So yeah, I was also thinking that these two could be merged into one. Yeah, in this raft consensus protocol, we have seen that it's part of only one request, right? In one request, they get a message to write the log, and also their response is has a meaning that they have agreed to commit the value. So whenever we will ask them to commit the value, they will commit the value.
Yeah, and it looks like in too fast commit, second database can answer no. Yeah, coordinator can ask to prepare, but database can reject. Yeah, can respond no, I cannot commit. Yeah, but in consensus it's not possible. Yeah, follower cannot reject message. What do you think?
Follower cannot reject the message.
Yeah, because in too fast commit, follower can say no, I cannot commit. Yeah, coordinator ask follower prepare. What can follower answer? Yes or no? Yeah.
Yeah.
But in concession, follower never can say no, I cannot.
Follower cannot say no. In yeah, okay. So if there is so if we are talking about the case of leader election, then in leader election we saw that one of the followers can say no to respond to vote, right? If it has already voted. But
Yeah.
in case of values, if a leader is asking a follower that save this value, yeah, I think the follower will not say no, that why would it not? But in database also, why would this node respond with no? Like why?
Oh, I don't know, because as I understand, there could be some issue, I don't know, with
Yeah.
disk or
Okay.
something like this. Maybe not enough memory or something like this. I don't know.
So yeah, I mean that could that same thing happen in the consensus also, that uh, the follower would not have enough memory to replicate the log, and so then that can also reply that I'm not able to commit the message,
Yeah, good point.
right?
Yeah,
So
right. But in this case, we will have not majority, yeah?
yeah, but yeah. So but in consensus, if it is not able to replicate, it could be fine as long as it gets the vote from majority.
In this case, they could the database too could reply no, because like there's already another transaction involved in that row, right?
Oh,
So it could reply no.
Yeah, okay. If that row is already logged by some other transaction, so then this will not be able to access this thing and it can reply no. But that seems less possible in consensus because there is only one leader, unless there is some other leader in the system. And yeah, I
So
don't
like
know.
if there's another leader, we already see like the network partition, right? There's would be two leader, but one leader cannot commit the data.
Yeah. But if one node is seeing the values from two leaders, so in case of a network partition, but in a network partition, in each partition, there will only be a one leader. So yeah. So a node will be seeing the values only from one leader, right? It's not possible. Is it
Yeah.
possible that a node is seeing value from two leaders?
they will have different term, yeah?
They will have different term. Yeah, they will have different term. Hmm. But okay, then it will yeah, so then it will then it will only reply to the leader who has who has the same term as this node's term, right?
Yeah, I agree.
Yeah.
Even if they have two different terms, when there's a network partition, they don't know. They don't know they have two different terms, right? Because if they on the lower side of the network partition, they only know that they belong to the same term as the leader, right?
Yeah. Mhm.
But
No,
like we already see that, like, we have two leader, but one leader cannot make a decision because they don't have enough vote,
yeah,
so
no,
they cannot
that
do the two-phase commit there.
I was thinking about some scenario. Let me draw that scenario. Uh, so let's say if these two nodes are leaders somehow and follower. So these two cannot talk to each other. So that's why they both think that they are the leader. Like there is some communication problem between these two, but they can talk to other nodes, right? So then this follower node can also receive a message from this node, and it can also receive a message from this node. So the example we saw in the book, in that visual, the partition was spread all across, uh, which meant that it was not hearing from this leader. But I'm saying it is also possible that only these two leaders cannot talk to each other because of some issue in the network in them, but they can talk to other follower nodes. In that case, this follower can receive message from two leaders, right? And but hmm,
I, you know, they, I don't think that is the network partition because they still talk to one the follower. Then if they can talk to one follower, then there should be only one leader.
Yeah, there should be, yeah, right. Because the leaders would have, these followers would have voted only for one leader. They cannot vote for two. Yeah. So I think, yeah, this is not possible. Hmm. Yeah. Okay. Okay. So the next topic is consensus algorithms and total order broadcast. Uh, so what we are saying here is that, like, many of the consensus algorithms that we will see, they are basically total order broadcast, and in the sense that they are trying to replicate a set of logs in the same order. And in the raft also we saw that raft is trying to replicate those logs in the same order, right? Which was what the total order broadcast was, that like all the messages, they have a strict order, and they are atomically replicated among all the nodes. So famous fault tolerant consensus algorithms. So these are some famous fault tolerant consensus algorithms: view stamped replication, Paxos, Raft, and ZAB. Most algorithms above don't directly use formal model described above, proposing and deciding on single value while satisfying. Instead, they decide on sequence of values, which makes them total order broadcast. So overall, Raft and all, they are like keeping those logs in the consistent state, right? Overall, they're keeping those set of logs in the consistent state. So that's why they are more closer to total order broadcast. And basically, total order broadcast is also similar to consensus in the sense that for each of the values of the log, right? If there are multiple messages in the logs, so for if you do a consensus on each of those message, then you can like replicate those set of logs among all the nodes, right? But there is one, okay, that topic will come later. Okay. To total order broadcast require message to be delivered exactly once in the same order to all nodes. So this is equivalent to several round of consensus for each message, right? In each round, node proposes the message they want to send next, and then decide the next message to be sent in the total order, right? So basically, total order broadcast can be made up by doing multiple round of consensus for each message, right? uh, so total order broadcast is equivalent to repeated round of consensus. Each consensus decision corresponds to one message delivery, and it follows all the four properties that we have discussed, that all nodes decide to deliver the message in the same order, right? Agreement, integrity, messages are not duplicated, validity, messages are not corrupted, and termination, that messages are not lost.
But can we discuss a bit why message could not be duplicated? Can if you are leader and send me message and I have not and I did not respond, can does it mean that you cannot resend will not resend message to me? Yeah.
So each message also has a log index, right?
Okay.
So even if I will resend the message and you already have a message, you will see that at third index you already have that message already.
Okay.
So
But
that,
how to ensure exactly one's delivery?
no, I mean exactly. So basically, it I'm saying that it might be possible that it's not exactly once, that a leader has sent a message to a follower and follower has written that message, but the acknowledgement did not got to the leader, right? So then leader will retry again, right? So the leader could try to send a message again, but then when the follower will receive that message again, it will see that at that index it has already saved that message. So then it will not duplicate on its end, like it knows it has the message already, but it will now this time respond acknowledgement again to the leader that I have written the message, and then the leader will not try again. Right? So in this way, we are not duplicating the message, and each of the followers will have message only once, exactly once.
Could you give an example of what is the total order broadcast?
So total order broadcast means that if we have a set of nodes in the system and they have like this node has M1, M2, M3, then total order broadcast say that this message in this same order, it should be delivered to all the nodes. M1, M2, M3 should be delivered here, M1, M2, M3 should be delivered here. So this is the total order broadcast, that the order of the messages should be same and it should be delivered to all the nodes. So we are saying that we can implement this total order broadcast through repeated round of consensus by first delivering M1 to all the nodes, and they all agreeing that they agree that at index 0 we will store M1, then similarly sending M2 and similarly M3.
Yeah, I think that we can implement total order broadcast because we have one leader. It's easy for us to interrupt. Yeah.
Yes.
Yeah, we
Right.
have leader, and leader will how to make a order of message. Yeah.
Yeah, right.
I think.
No, but the point is, so one thing I want to mention is, so consensus means that all the nodes should agree on some value, one value, right? Raft is a implementation of consensus, and Raft implements consensus by choosing a leader, and that leader will make the decision. But that is not same with all the consensus algorithm, like the Paxos algorithm. In Paxos, there is nothing like leader kind of thing. So in Raft, they want to simplify it, and they said that it simplifies a thing a lot when you make a leader and leader is taking a decision. But if you will consider Paxos does not has this one leader thing, but still it can also implement consensus.
Oh,
So
very interesting.
yeah, but then also it is very hard to understand. So people say that Paxos is very hard to understand.
Oh, I see. Very, very interesting. Yeah.
What would be the use case of using the total order broadcast? Because I can see that if we do the total order broadcast, it can be slower, right? Because we handle the leader have to handle one message at a time. Versus if we don't do the total order broadcast, the leader can send message 1, 2, and 3 simultaneously to all the node.
Mm.
That would be faster, right?
Yeah. But as I understand, we need total order. If we have total order broadcast, we can have strong consistency, linearizability.
Yeah.
And what I think is, maybe even if the message arrive in out of the order, the notes may have a condition in them, like process them in order, so they quickly know, okay, this message has the, like for example, if we have not received M2 and got the M3, in the processing they might have a condition like, okay, if we have not received in order, just don't process, just wait.
Yeah. Yeah. Mhm. I think that is done by like, yeah, by like this will specify the order of the messages. So yeah, if the message is not in that order, like uh if this node receives M1 and then it receives M3, then it will not put M3 in its log, because it will see that the log is like, this log will have index 0, this will have index 2. So it will say that I have a log missing at index 1. So first I need a log at index 1. So that's why it will not write.
Okay.
But
Yeah,
Leon's
I think
point is,
it go ahead.
no, I think you were saying that why don't they send all these three messages like as one entity, right?
Yeah.
Yeah. Mm, mm.
Yeah, I think that because yeah, I think because of the we want the cause causation, right?
Yeah.
Causation message. We want to know what happened before.
Yeah.
So that's why we have to do this way, total order broadcasting.
Okay. No, but if these messages, yeah. Okay. Mhm.
But total order broadcast is strictly consideration than happens before. It's more strict. Yeah.
Yeah, it's more strict. Yeah. It has like a total order of the messages, more stricter than the causal order. Okay, so this thing is very interesting. So okay, now this is the question for everyone. So uh, we usually say that leader election requires consensus, right? To elect a leader, you need a consensus uh, that like that all the nodes should agree who the leader is. Now, if you consider the case of Raft, Raft is solving the problem of consensus, right? Raft is an algorithm to solve consensus. But to solve the consensus problem, first it needs a leader. And to elect a leader, we need a consensus. So basically, Raft overall is an algorithm to solve consensus, but to start, to actually elect a leader itself, it needs a consensus. So how does this thing is taken care of? That an algorithm which wants to implement consensus, but to actually elect a leader itself, first it needs a consensus. Uh, did you understand and see the problem? Like, what is the problem?
The, the chicken and egg problem.
Kind of. You can say like a chicken and egg problem that. Uh,
So here, leader election, we are not talking about the external systems that are using the protocol to do a leader election, but instead how the protocol is deciding the leader, right?
Yep, how the protocol is deciding the leader. Yeah, it's correct. Not an external system. Yeah, but that leader would be seen by external system also. Yeah, but
I mean, the way they deploy, they can start deploying, okay, let's deploy just one. I mean, if we have a five nodes uh, in our raft cluster or something, instead of starting five at the same time, start one by one.
Mhm.
So the first guy is gonna become a leader because we have given him a early start.
So sorry, what's the point if we have five nodes and
I mean, when we start the cluster for the first time, right? That's when this problem is we are discussing, correct? Like, like we are
not
starting up the cluster. Who is the leader?
not during the start also, but if a leader fails, then also you need to elect a leader. At any time, you might need to elect a leader. Okay, so before we go there, let's first answer a simple question. What is the difference between consensus and quorum? Can anyone tell what is the difference between consensus and quorum?
Consensus means to have agreement on one particular value, and
Right.
quorum is to have a majority.
Right. Yeah, your point is right. Yeah, basically, yeah, it's right. To explain more, like, so basically, consensus means that everyone should agree on one particular value, right?
Yeah.
And that could also, a system could also be a consensus system without the majority. Like if it is kind of a dictator, kind of where there is, we have decided, like we have manually decided that this node is a leader, and now this leader will take all the decision. So even if like other nodes might not have agreed, but
Oh,
overall as a system we have said that we don't care about your majority, we don't need your majority, we are choosing in a dictatorship way, and in dictatorship is the manual administrator. So whoever is the administrator and he says that this node is a leader, then this node will be a leader and it will take all the decisions, right? And
yeah.
now because it will now take all the decisions, so all the node will now agree and listen to its value and uh, come to one conclusion. Whereas when we are saying quorum, quorum means that majority, that like a decision will be made only by the majority, and it's not like there you cannot have a dictatorship kind of thing. So
Okay, so does it mean that in order to implement consensus, we need a quorum?
so so yeah, that's what we are saying. The single leader system, they also have a consensus, right? But they don't have a quorum where a leader broadcasts message to all the followers. uh,
Okay,
so that is also kind of a total order broadcast, right? But the thing is, the so basically in this fault tolerant consensus, so the difference is in fault tolerant consensus, like you don't have to manually intervene the system will automatically choose its leader. And how the system chooses its leader is by doing quorum of votes and deciding who the leader is. But if you don't want such kind of a system, you can also have a system where you are deciding the leader, and then that leader is doing like, and then the system is in consensus in the sense that everything goes through the leader. Whatever the leader is saying, all the followers have to follow it, and the system is still in consensus.
Then who would decide the leader? Is that the administrator?
Yeah, so the
Would
administrator is deciding the leader, and so that's why it's not a fault tolerant consensus, because the system will not automatically be able to tolerate fault if the leader goes down. Then because then the admin has to step up and decide who the new leader is. So let's read through this again so that we can understand better. So leader, in single leader, this single leader replication, which we have discussed in replication chapter, leader broadcast message to all the followers. So isn't this a total order broadcast, because now the leader is sending message to all the node? The issue is about how to choose leader. If a leader is chosen manually, then the consensus is of dictatorial way, right? If a node goes down, system becomes unavailable unless manually intervened and the new leader is chosen. So in this case, it is, so we said that fault tolerant consensus, it should satisfy these four values, right? So if you are manually choosing the leader, your system is satisfying first three values, but it is not satisfying fourth value. So it does not satisfy the termination property of fault tolerant consensus as it requires human intervention, because basically your system now will, we are saying that the system should decide some value. But now if your leader is down and if you are manually choosing a leader, then your system will not be able to decide any value because there is no leader, right? So that's why your system will never terminate. And although whenever the system was working fine, then these properties were satisfied. But if the system is down, then it is down, and then your messages will never terminate. So databases that do automatic failover need to elect leader and implement consensus. So, but if you don't need a manual intervention, if a database need automatic failover and a leader election, then it needs to implement consensus uh, using a fault tolerant way, where it is decided based on the quorum of values that who is the leader. So now this is basically a kind of going in circle that uh, basically these consensus algorithms are needed to elect a leader, right? And we saw that the consensus algorithm itself, it has to elect a leader to actually come to a consensus. So the answer to this question is that uh, like in these algorithms, the leader election consensus is not a strong guarantee. Uh, Basically, in consensus, we are saying that everyone should agree on the value, right? But in the leader election, there is no strong guarantee. So all consensus protocols uh, discussed so far need a leader, but they don't guarantee that the leader is unique. Instead, they make a weak guarantee. So these protocols define an epoch number and guarantee that within each epoch, leader is unique. And this same thing we saw in the raft when there was a network partition, right? So if the leader election was like strictly consensus, then all the nodes should have agreed on one leader, right? But in case of network partition, we saw that the system was thinking there was two leaders, right? But you will see that the system will never agree on two values. Overall, the system will always agree on one value of the system. Like if you are sending a value 5, and whether to accept or reject the value, the system overall will agree only on one value, that whether to accept it or not to accept it. So overall, it will maintain a consensus. But the part where it is electing a leader, there it is only a weak guarantee, and there might be multiple leaders, which we saw in the case of network partition. But at least they guarantee that within each term, so they define a term, and within each term the leader will be unique, right? And so basically overall consensus is reached by the overlap of both, that the leader should also be of the same term, and if the message, so the leader also needs a quorum and it should be of the same term, and the message that is um, that has to be acknowledged, that should also uh, be agreed upon the leader. If both of the things happen, then only the system will reach overall consensus. So in the network partition case, we saw that the lower part of the system, although there was a leader, but it was not able to reach the consensus in the value, right? And so that's why that value was not acknowledged by the system.
Can you
So,
go back to the whiteboard? There you made a system up
mhm,
where there was network partition between the two nodes. Here,
mhm.
this you said that T1 can never become a leader. I think it can become a leader. because when T1 will not get heartbeat from T2, it will time out and then it will become a candidate and will ask for vote from both the other nodes. And then those two nodes can say yes, and T1 can become the leader.
Okay. So then this one will become leader and its term will be T3. So then, okay. And then this leader will now, yeah, right. So now this one is also leader and this one is also leader. So now I think what will happen is they will see that this node, the follower node has a leader from term 3 and this follower also has a node from term 3 because they have agreed on this is the leader, right? And so now if T2 still thinks that it is a leader, if it will send a message to these nodes, I think in this case, they will not acknowledge its messages because they will say that there is already a leader with a higher term that we know of. So we will not accept your messages. So the messages of this leader will not be accepted. Yeah. And basically I think then in this case the leader will keep on switching because then this node now will not, so this node is not able to send its messages, but also it will not receive a heartbeat from this leader, right? And because it is not able to receive the heartbeat, so it will see a election timeout and then it will start to ask for votes. And because this can actually take votes from these two nodes, so now this will get votes and now this can become a leader. So yeah, so then this will become a leader for term 4 and this will keep on switching.
Yeah, makes sense.
Okay, I think we are out of time. So yeah, so next time probably we will discuss the limitations of consensus. And also then we can discuss about the membership and coordination services. Okay, thank you everyone.
Thank you.
Yeah, thank you, Abhishek. Yeah.
Thank you very much. Bye. Thank you.
Yeah, thank you.
A quick question, which group was it? I mean, which group channel in the Discord is it?
Sorry, are you talking about this session which was happening right now?
Yes, yes.
Oh, it's a book club session. So every Saturday, 7:30 a.m. PST to 9 a.m. PST, we have a book club where we are discussing about designing data intensive applications. So we are discussing that book, and right now we are on chapter 9 of that book, which is consistency and consensus. So we were discussing.
Okay, great. Thank you, Abhishek, for the explanation.
Where can I find older recordings, recording of previous chapters?
So the recordings are on this SDE Skills YouTube channel, and right now I think we have recordings till chapter 7, which is transactions.
Hey Abhishek, your recording from the previous session is still happening?
No, I have stopped it.
Oh, it looks like it's still running.
Is it? Oh, sorry. I think I have stopped sharing the screen, but not the recording.
Okay.